Okay. So, I want to, in today's lecture, I want to introduce 3 important notions, maybe more. So, first is the notion of the orders and average orders of functions. And our focus in this course is, of course, arithmetic functions. Then we discuss in detail the idea which we know, which we are all familiar with, namely that there are infinitely many primes, and as we had discussed last time, this has an analytic interpretation. So, what we study is the following: sum of the fractionals of prime numbers up to x. We show in a very refined form that this goes to infinity as x goes to infinity. In fact, for a given x, we find fairly sharp estimates for this. Okay. So, this is a very fundamental identity, and it is a sharper way of saying that there are infinitely many primes. And finally, we are going to apply this identity today to study the average order of a very interesting arithmetic function, namely omega n, which is the number of distinct prime divisors of n. So, let us start with the first topic, namely orders of functions. We are going to introduce a few symbols which are going to be our good friends throughout this course and very helpful to understand or to express what we know about growth of certain types of functions. So, let us take functions f and g. Let us say f is it's a function defined on the real numbers, but it could take complex values, and let us take g to be a real valued function which furthermore beyond a certain stage takes only positive values. So, such that g of x is positive if x is greater than or equal to a for some specific a in R. Okay. Now, we do not necessarily have to take functions defined on R, we could also take arithmetic functions. So, functions which are defined on the set of natural numbers and compare them. If the function looks very weird to us, we want to be able to use analytic techniques so that we can compare that arithmetic function or a function defined on R to a function that looks nice, that we understand well. So, we say that f of x is big O of g of x, okay, if there exists an absolute constant, or if there exists a positive constant m such that absolute of f of x is less than or equal to m times g of x for x greater than or equal to a. So, let us say you have a real valued function g which takes positive value beyond the real number a, and we have this condition that absolute f of x, see f can take complex values as well, but absolute f of x is telling you about the size of f of x. It is at most a certain scalar multiple of g of x. Okay. So, we are not just talking about the situation when absolute f of x is less than or equal to g of x. Let us say there is some scalar constant, maybe 2 or 3 or something like that, so that this inequality holds. This is also good for many purposes, and when this condition holds, we say that f of x is O of g of x. This is an important symbol. Want to make two observations about this symbol. Firstly, suppose you have two functions, say f and h, such that f minus h absolute of f minus h. So, is less than or equal to some m times g of x for x greater than or equal to a. Suppose we have this condition, then we can write f of x to be equal to h of x plus O of g of x. Okay. The other remark that I want to make, and you will have opportunity to use this, if f of x is O of g of x, then provided your g is a function which takes positive value for x greater than or equal to a, then integral from a to x f of t dt can be shown to be O of the integral from a to t of g of t d. I am going to leave this as an exercise for you to verify. Okay. So, in this sense the integral respects the O symbol. Now, so this is the first definition. F of x is big O of g of x. This is one way of representing an order of a function. We also have another notion. We say that f of x is little o of g of x if the growth of f is really small as compared to g. This is telling you that the growth is bounded at most by the growth of g, but here this is a stronger notion which tells you that limit as x goes to infinity f of x over g of x is 0. Again we are starting with f and g as before. Okay. So, what this tells you is that as x becomes very, very large, f in relation to g, the size of f is very small. This, by the way, is of course equivalent to saying that limit of absolute f of x over g of x goes to 0. Now, a quick exercise for you to verify that this little o is a stronger notion than big O. So, if f of x is little o of g of x, then you can also write that f of x is big O of g of x, but this is weaker. Okay. The converse is not true. I will let you think about this exercise. Now, one other notion is that of asymptotic. So, we say that f of x is asymptotic to g of x as x goes to infinity if in the asymptotic limit as x goes to infinity, the ratio f of x over g of x is equal to 1. As we proceed, we will see some very special examples of these phenomena. So, these are three different notions to study what are called orders of functions. Okay. Please go through these notions carefully and learn to use the appropriate symbol at the appropriate time. Now, we talk about what is called an average order of a function. Okay. Now, before that, I want to actually give you a couple of quick examples of the first notion, which will be useful for us. First is, so let d of n, given a natural number n, little n will always denote a natural number in our course. D of n is the number of positive divisors of n. Okay. Now, if you think about this, this function will fluctuate a lot. Suppose n is a prime and we just saw that there are infinitely many primes, d of n would just be equal to 2. But before a prime or after a prime, you could have a composite number with many divisors. So, this function is not the growth per se, or rather the values as n keeps changing are not very smooth, they fluctuate a lot. So, what we want to understand is, in general however, how does this function grow? Now, at a very elementary level, suppose you write n to be equal to a times b, then either a has to be less than or equal to root of n, or b has to be less than or equal to root of n, right. If they are both greater than root n, their product has to be greater than n. So, this observation helps you to derive the fact that d of n is less than or equal to 2 times square root of n. So, the number of divisors of any n is bounded at most by 2 times square root of n. In other words, you have this bound d of n is O of root n. D of n is equal to O of n was obvious, right. So, here you can actually refine this bound, and this is a more involved exercise which we will actually do in our next live session. So, d of n, you can show that it is not just root n. Suppose I were to take n to the 1/3, d of n can be shown to be O of n to the 1/3. Suppose I take n to the 1/4, suppose someone takes n to the 1/10, or someone even chooses to take n to the 1 over a million. My claim is that you can still find some a large enough so that d of n would be O of n raised to the 1 over million or 1 over 10 million or whatever. So, this is what we are saying. Let epsilon be any positive number, however close you want it to be to 0. Then you can show that d of n is O of n raised to the epsilon for any such epsilon, whatever epsilon you may choose, 1 over 10th, 1 over a million or whatever. Okay. So, it can be made very, very small. Another exercise that I would like you to think about is the function, the logarithm function. You can actually show that log of n is also O of n raised to the epsilon for any epsilon greater than 0. Okay. So, as compared to any tiny power of n, log n is O of that function. Okay. Another observation I just want to make, another notation for f of x equal to O of g of x okay, it can also be written as f of x is less than g of x, a slightly more a slightly wider notion than that of less than or equal to. So, we term it, we denote it by what we call less than g of x. So, these are two notations, and depending on my mood or whatever the situation requires, I may alternate between these two notations. But in general, I mean, it is not just about my mood, in general in different textbooks you will see these two notations being used interchangeably. All right. Now, as I mentioned, this function d of n fluctuates a lot. So, we may ask, fine, what is the mean of this function or what is the average value of this function? So, let us take the following. Let us take summation n less than or equal to x d of n, and let us ask how this function grows. Okay, let us say this is, you call this capital F of x. How does this function grow with x? So, while the divisor function itself fluctuates a lot, we want to know how do the sum of the divisors up to x for all the natural numbers up to x behave. So, what you do is you write this as summation n going up to x, and the inner, so this sum is d of n. That means for any divisor of n, you can choose the value 1 and sum this up over all the divisors. So, what we do is we take all possible divisors of n, and for each divisor, to each divisor we attach the weight 1. So, small remark, we say that A divides B. This is a notation that is frequently used in number theory. If A divides B, this is the notation, okay, A bar B. So, going back to the sum that we are trying to study. So, what do you have? Let me just rewrite this. You have sum over all the n's up to x, and then in the inner sum, for every n you are taking all possible divisors, and to each divisor you are attaching the weight 1. Now, this is a finite sum, so you can interchange it. So, for what are you doing? You are running over all integers up to x, and then for every n you are taking all possible divisors. Now, if n is less than or equal to x and d divides n, that means that d itself has to be less than or equal to x. So, let us do the opposite. Instead of taking all the numbers up to x and then every possible divisor for each of them, let us take all possible numbers up to x, and for each of those numbers, let us also take all possible multiples of that number which are less than or equal to x. They will count exactly the same quantity, you are just counting them in a different order. So, what are we doing? we are taking first of all possible numbers up to x, okay. And then in the inner sum we are counting all those multiples of d which are also less than or equal to x. That is, you are counting all those natural numbers e such that d times e, for each d that you have chosen outside, you are counting all those e's so that d times e is less than or equal to x. All right. So, what do you have here? Summation d less than or equal to x, and in the inner sum you have all those e such that e is less than or equal to x over d. So, how many positive integers do you have up to x over d? This is counted by what is called the greatest integer function, which you denote by box. Okay. Sometimes you just denote it by a floor function. Okay. There are different notations, we are going to just use this box x over d. So, for example, how many natural numbers are there up to 31.351? It is just 31, right, which is exactly the greatest integer of 31.351. So, we have this, and then we observe the following. The greatest integer function x by d. Notice here is a very basic but important fact that you learn. Suppose you have some real number, okay, in this case positive, you can write this as the greatest integer of x plus the fractional part or the decimal part of x. And what do you know about the fractional part? It has to be at most 1, right, strictly less than 1 and greater than or equal to 0. So, you can write this expression box x. So, what you have is box x is equal to x minus fractional part of x, which you know is x plus O of 1, because absolute of minus fractional part of x is bounded at most by 1, right. So, basically this is a precise way of saying that box x by d is very close to x by d, give and take a small constant. So, x by d plus O of 1, right, and this can be further simplified as x times d less than or equal to x 1 by d plus, what are you left with? You have O of 1. So, you are summing over all the d less than or equal to x, okay, and in the sum you have something which is at most some constant, right. So, therefore, summation of O of 1 as you run over all the d up till x is at most O of x. So, this is O of x, and by your integral test that we discussed in our last lecture, this sum is very close to log x, right. And in fact, so you can compare this sum to the integral of 1 by t dt from 1 to x, okay, with a small error term which is absolutely bounded above by some constant. So, turns out that this is just log x plus O of 1, and you already have O of x outside. So, this is x log x plus x times O of 1 can again be written as O of x, okay. This O of x and O of x when you have some function which is O of x and another function which is O of x, and you sum them up, you get again a function which is O of x. So, this is O of x. We are not worried about the constants in our estimates. Okay. For certain applications, we have to keep a good track of all the constants that also appear. So, when the need arises, we will do that. So far, what have you studied? What this tells you eventually is that thus summation of d of n is x log x plus O of x. And therefore, if I were to ask you to tell me what is a mean value or the average value of d of n up to x, what you will say is that 1 over x summation n less than or equal to x d of n. Okay. Even if you can't give me the exact value, you will say that it is log x plus or minus something small. So, O of 1. In other words, what this is telling you is that the average order of d of n appears to be something like something very close to log x. In fact, it is asymptotic. Log of x plus O of 1 is asymptotic to log x as x goes to infinity, because when you divide this term by log x, here you have 1 log x by log x, and O of 1 by log x is going to 0 as x goes to infinity, right. So, since this is one of our initial lectures and some of you are seeing number theory for the first time, we will emphasize on some of these basic facts, and within a couple of classes you will become very familiar with this language. So, what we get is that average order, not the order, okay, but the average order of d of n we say that the average order of d of n is log n, okay, because the average value is something. So, this over here you have log x. So, in other words, what we say is the following. So, here is a precise definition of the notion of average order. So, let f and g be as before, okay. In particular, so let f be an arithmetic function which could possibly take complex values, and g be a real valued function which takes which is positive for okay, it's at some point this function just becomes positive and remains positive. Then we say that g is the, so we could have the way we are defining, yeah, it is the average order of f if summation n less than or equal to x f of n. So, on average this behaves like g of x plus something left over. It may not be an exact equality, but whatever is left over is actually something very small. Okay. So, plus something which is much smaller, little o of what you are taking to be the average order. Okay. So, the function g of x plus an error term which is of a much smaller order than the main term itself. So, in this situation we say that g is the average order of f, and in particular we just saw that log n, okay, log n is the average order of d of n. This is the example that we just saw. D of n. Now, of course, this begs the question, it is the average order, but how does d of n vary with respect to its average order? How does it fluctuate? Okay. So, there is a probabilistic way of stating this question. So, what we do is, suppose you have, let us take 1, 2 up till capital, some natural numbers up till capital N. Okay. Let us take a set and let us consider this set as a probabilities space. Okay. So, what we the probability defined here is the uniform probability. So, the probability of any I is just 1 by n. Okay. So, all of these points in this space have equal probability, and I am going to make this even more precise soon, but with this, if you consider this space as a probability space, the average order, okay, and let us say let f be some, let's call this x. Okay. So, let this be a probability space with the appropriate probability measure, and let f from x to c be a random variable okay. So, in that case, for example, f of I is, let us say, the divisor function of I. So, this is a specific example. So, now the question is, when you talk about average order of a function, what you are actually asking is essentially what is the expected value of this random variable, right. So, this is 1 over n summation all the I going from 1 to capital N f of I. And what we have just seen is that as n, capital N goes to infinity, this is actually asymptotic to log n. So, now the next question, when you talk about expectation, the next question to ask is what is the variance? Okay. So, V of f by definition is 1 by n summation I going from 1 to n, right. You are trying to understand how does your function f deviate in terms of around, how does it deviate around its expected value or its mean or its average order. So, what is this? So, f of I minus square. Okay. Now, you know that this expected value is asymptotic to log n for very large values of n. So, related question is, if you as n goes to infinity for large values of n, what is the difference between f of I minus, so in particular your f is just the divisor function. So, d of I minus log n whole square. These two questions are related to each other. Okay. So, this is how probability starts to enter the picture when you are trying to understand orders and average orders of arithmetic functions. And so, we will continue on this theme, but instead of focusing on the number of divisors, we are going to study another very special function, namely the number of distinct prime divisors of n, and study these notions for those, and that is actually at the heart of the developments that led to use of probability in number theory, or the subject that many like to call probabilistic number theory. Before going to that function, there is another useful identity which I mentioned at the beginning of the class that I want to discuss. So, we want to study the following sums. So, in our class, whenever I write little n, I refer to a natural number. Whenever I write little p, it refers to a prime number. So, this is what we want to study. We want to understand the growth of this function. Now, many things go into the study of this sum. So, last time we had looked at certain other functions which are related to our study of distribution of prime numbers. So, we are going to invoke them again. So, here are some fundamental themes in this study, okay, which all of them are useful summation techniques in their own right, and we are going to put them all together in the right order to derive information about the sum. So, first is, so here is a technique. So, last time you learned how to study weighted sums a of n times f of n, where a is some arithmetic function and f is some nice function. Let us say, by nice I mean continuously differentiable in some region. So, let's just write this. Okay. And so, this of course, that can be generalized to any arithmetic sequence. Okay. But there are some other refined techniques which actually relate these sums. So, suppose you have weighted sums of f, okay, with respect to certain other two different types of weights. They can be in certain situations, information about one sum leads to information about the other, and the class of theorems that does this are called Tauberian theorems. So, we are going to mention one particular Tauberian theorem shortly and use that to study this sum, and we will prove that Tauberian theorem in our next live session. Now, the other important thing, so we learnt last time, let us quickly recall this function lambda of n, this is log p if n is some prime power, any prime power, okay, not just a prime, but any prime power. But if it is not a prime power, then this function takes the value 0. Another function that we learnt, and we saw that the partial sums of these two are asymptotically the same by an application of the partial summation technique. This is log p exactly when n is a prime and 0 otherwise. Okay. So, we studied these functions and how they are related to the prime counting function. Now, let us make some nice observations about these. Firstly, my claim is for any natural number n, suppose I were to take summation of lambda of d, okay, as you run over all the divisors of n, this turns out to be equal to log n. Why is this true? So, suppose you write n to be equal to p1 raised to the a1, p2 raised to the a2 up till p sub k raised to the a sub k. You know that any number n has a unique factorization in terms of its prime power, in terms of prime powers. So, let us say this is the unique factorization. So, pi's up till from I going from 1 to k are the prime divisors of n, and these are the respective powers to which they divide n. So, now when you talk about lambda of d, so suppose you have a divisor d of n, for which divisors of n will lambda of d actually pick up positive values? Only when your d is of the form p raised to the a, where p is one of these primes and a is something less than or equal to a sub I, right. So, for example, it will pick up a positive value log p1 at p1, it will pick up log p1 again at p1 square, p1 cube, p1 to the 4 all the way till p1 to the a1, right. So, what you have is that this sum lambda of d is for each I going from 1 to k, you have log of pi, it picks up log pi how many times? ai, many times, depending on what the power ai is. But this you immediately see is just your log of n using properties of the logarithm. So, this is your first like it's a nice identity. Okay, let's call this, let's label this as equation A for the purposes of today's class. Now, let me now ask you what happens to this sum log n. Suppose you see we have been learning different types of summation techniques. Suppose I give you this sum and I ask you to evaluate its order or give me some estimate for this function. You can automatically apply your partial summation technique, which will compare this sum with integral of 1 to x of log t dt, and with the use of the partial summation as we had stated it last time, you can verify that this turns out to be equal to x log x minus x plus O of 1. Okay. In fact, you can also make this even more refined by writing a constant plus a function of a lower order, but we do not need that right now. Just by your partial summation technique, you can actually derive this. Okay. I am going to leave this as an exercise for you. Then what this tells you is that this sum, however, by what you wrote above, is also summation d dividing n lambda of d, right. So, let us now look at the following. So, let us evaluate this. Again, you have a double sum. So, you know that you have to do an interchange of summation. So, this is equal to, first you sum over all the natural numbers up to x, right, and then for each such natural number you need to consider all the multiples dE which are less than or equal to x, exactly as we had done when we were looking at the average order of d of n. So, what do we have here? D less than or equal to x, lambda of d, and the inner sum is exactly x over d. So, this tells us that combining this with identity A here and the partial summation, what you end up getting is that this is equal to x log x minus x plus O of 1. Now, let us study this more carefully. Lambda of d is picking up logarithms at prime powers. So, this sum now, what does it do? Let us break this down into two parts. One is just going over the primes and the other one is going over prime powers p to the k, where k is at least 2. So, let us take p less than or equal to x, lambda of d in that case is just log p times the greatest integer of x by p plus the second part of this sum goes over, as I mentioned, the prime powers. So, let us go over all the k greater than or equal to 2, okay, such that your p to the k is less than or equal to x. So, all the primes p such that p raised to the k is less than or equal to x. Okay. Even if you have p square or p cube, this is just picking up the value log p. So, this is just log p. In the box function, however, you have to write x over p raised to the k. Now, as discussed in our previous class, the sum corresponding to higher powers of prime do not contribute much to this sum. So, here what we observe is the following. We observe the following. If you let me write it here itself. So, suppose you have the second term, okay. This term here is less than or equal to summation k greater than or equal to 2 summation over all the primes such that p k is less than or equal to x log p times x over p raised to the k. The greatest integer is always less than or equal to x by p to the k. Now, I take x out and then what are you left inside? I first write, so I do an interchange. So, let me run over all those primes p I need to take p's which are bounded above by something, which I will specify later if needed. Okay. And for each such prime p, what do you have? You have an inner sum going from k to infinity. Since there is a less than or equal to, you can actually go as long as you want, because each of the terms here is contributing a positive weight. So, you have 1 over p to the k You all know how to evaluate this. This is a geometric sum. So, what you have is the above is x summation over p log p over p times p minus 1. I will let you verify. The sum turns out to be exactly equal to 1 over p times p minus 1. Now, what do you have? You seem to have a sum. Okay, it is a finite sum actually, it is bounded above by something finite, but even if it were infinite, what do you have? You have x times something which you know it is certainly less than or equal to summation over all the n's log n over n times n minus 1, let us say going from primes start from 2, right. So, what do you have here? Log n over a function which is close to, which is of the order of n square, because this is n square minus n, this is certainly O of n square, right. So, what you have is less than x times summation n going from 2 to infinity 1 over not 1 sorry log n over n square, which furthermore is by an exercise that I wrote for you, log n is less than n to the epsilon for any epsilon. So, in particular you can take epsilon to be equal to half, and you know that this is certainly less than log n is less than n to the half. N to the half over n square is just 1 over n raised to the 3 halves, and this is good because we know that this sum definitely converges to an absolute number. So, this is certainly less than x times an absolute positive constant, and so you have this is just less than or the big O of x. So, all this work, what this basically just shows is that the second term here is just O of x. Thus, what does this tell you? It tells you that, let us summarize this. Suppose you start with the right hand side here, x log x minus x plus O of 1 is equal to summation p going to x log p times x over p plus O of x. And therefore, this gives us an estimate for this sum here. So, we conclude that thus our summation p less than or equal to x log p times x over p is equal to, what is this equal to? X log x minus x plus O of x, which moving to the left hand side does not become minus O of x, it is still O of x. So, when O of x comes to the left hand side, your precise term minus x gets absorbed in that, and O of 1 is obviously of a much smaller order than O of x. So, this ends up telling you that. So, this is an important estimate that we will use a lot in this course. At this point, I am going to recall a theorem, a Tauberian theorem. It is called a Tauberian theorem, but it is due to Shapiro, proved it in 1950. This is all these are very classical estimates. So, what did they show is that suppose you have, so the Tauberian theorem states the following. Suppose we have a sequence of non-negative real numbers, okay, be contained in, so R, but the non-negative. Suppose you have such a sequence, okay, then, and you know that a certain weighted sum of these sequences with a specific function can be estimated. Suppose you know that given such a sequence A of n of non-negative real numbers, A of n box x by n, suppose you know that this is equal to x log x plus O of 1. Okay. In that case, this theorem claims that you are able to deduce that basically what this, sorry, not O of 1, O of x, suppose this is what is given to you, then under the condition that A of n's are non-negative real numbers, you can actually cancel off x from this equation. So, what this tells you is that n less than or equal to x, A of n over n is equal to log x plus O of 1. All right. So, this is your Tauberian theorem that relates both these weights to each other. We will prove this in our live session, but for now we are going to use it for our purposes today. So, this tells you, now what you do is choose application of this theorem. Choose A of n to be log p if n is a prime and 0 otherwise. The left hand side now it becomes summation p less than or equal to x log p times box x over p, which you have already evaluated, and it is exactly equal to the form which you require. We are given, we know already that this sum is equal to x log x plus O of x. What does this mean? So, by the theorem, we derive that summation p up till x of log p over p, which is your function summation n less than or equal to x A of n over n, since it picks up values only when n is a prime. This turns out to be exactly equal to log x plus something which is absolutely bounded. And from this now you can apply partial summation again. It becomes a standard application, and I will let you fill in this detail. Summation of, from this you can derive that summation of 1 over p. How will you apply partial summation? What you can do is you can take A of n to be equal to log n by n if n is a prime and 0 otherwise, and take the function f of x to be equal to 1 by log x. Then summation A of n f of n turns out to be exactly this sum, and then you apply your partial summation. This will turn out to be equal to log x plus O of 1. This is a very important identity which is now going to be very useful for us. And of course, as I mentioned before, this is actually a very sharp and refined way of telling you that as x goes to infinity, this sum also goes to infinity. So, this sum diverges, an analytic way of saying that there are infinitely many primes, but the reason why this is sharper is that it is actually telling you, giving you precise information for the growth of this sum as a function of x. So, rather it is telling you how the partial sums are growing at every stage. Now, we move to the function that we want to study for today. So, just like, sorry for the harsh example, but just like every pandemic has a patient 0, right, every nuclear detonation has ground 0, similarly probabilistic number theory also has a theorem 0, because the entire field basically comes out of this theorem, but of course, this theorem 0 has happy consequences. So, what do we do? Let us define omega of n is defined as the number of distinct prime divisors of n. You can also consider a related function where you are going to study the number of prime divisors along with their multiplicities, but for now we just focus on the number of distinct prime divisors of n. So, now the question is, how does this function behave on average? Okay. So, let us derive that quickly. We have set all the tools already for this. What is the average order? What is this average sum? So, what do we do? This is summation as n runs up till x, right, and omega of n, what does omega of n do? It is actually the partial sum, it is the sum of a function which takes the value 1 at a prime and 0 otherwise. Okay. So, what you have is summation over all the primes dividing n 1, the inner sum can be written in this form. When you were talking about the average order of d of n, the inner sum was running over all the divisors of n, but here we have the inner sum running over only the prime divisors of n. But other than that, the technique to evaluate this is exactly as in the average order of d of n. So, the inner sum, so outer sum runs over all the n up to x, inner sum runs over all the primes dividing each n coming from the outer sum. So, if you want to interchange, what do you have? Now, the outer sum will run over all the primes up to x, and the inner sum will run over all the numbers n up till x which are divisible by the prime p, right. So, in other words, it runs over all the multiples, it runs over all the e's, so that the multiple p times e is less than or equal to x. And again, this is the inner sum is something that you now know how to write. So, you have summation p less than or equal to x. What do you have here? X by p. We just studied lots of theorems about sums of this form, and furthermore, what you have is p less than or equal to x. So, this you can write it as x by p plus O of 1, right. And so, now you are just left with a main term that involves the sum of the reciprocal of primes, which we pretty much spend the entire hour learning. So, you have this is equal to x times summation p going over all the primes up till x 1 over p plus you have O of 1, but the outer sum is running over all the p up till x, which is certainly less than or equal to x. So, a rough estimate of this form will be sufficient for us. But then you just learned that this sum here is log x plus O of 1, which you multiply by x. So, overall you end up getting log x plus O of x. So, the average order of omega of n, now I don't, since we actually have defined the average order precisely, the average order of omega of n is log n. Contrast this with the average order of the divisor function d of n. The average order there was log n, here the average order is log of n, which is significantly smaller. So, this now leads again to the question when you interpret this in a probabilistic format. So, now suppose you again, as mentioned before, suppose you have this space of natural numbers up till capital N, which you are equipping with the uniform probability. What this is telling you is that the expectation, and so suppose you define f from x, actually this is it's taking very specific values where, so f of n is just omega of n. Okay. So, what we wrote above is telling us that the expectation of f is asymptotic to log capital N as your space capital N, your capital N becomes larger and larger, and so it leads to the question about what is the variance. So, now the question is, what is n less than or equal to n, or variance in the asymptotic sense. So, what is omega of n minus log n. Let us take the square of this and ask what is the average order of this 1 by n. Okay. And this is where we enter into probabilistic number theory. So, what is the theorem 0? Theorem 0 is actually a very famous theorem of Hardy and Ramanujan, although their motivations were different and they were not studying it from the probabilistic viewpoint. In 1917, they proved that the above estimate is suitably bounded above, and whatever they proved, I am going to tell you in detail in the next class. A simpler proof was provided by Paul Turan in 1934, and at the essence of both these theorems is the assertion that the above sum 1 by n summation n less than or equal to n omega of n minus log n whole square is less than or O of log n. So, variance is bounded above asymptotically as n goes to infinity by log n. So, the deviation from log n is at most of the order of root log n. Essentially this is what this theorem is saying, and there is a more refined theorem due to Erdos and Kac. So, as you all know, Erdos is known as the man who loved numbers. There is a book for small children on Erdos. It is called The Man Who Loved Numbers. I just gifted it to my 4-year-old nephew. And then for grown-ups, there is a book called The Man Who Loved Only Numbers. So, that is Erdos for you. And Erdos-Kac theorem says the following. It says that this limit as n goes to infinity of it predicts the probability of what bounds this function can take. So, this limit of 1 by n of the number of n up till capital N for which omega of n minus log n over square root of log n what is the number of little n's up till capital N for which this takes the value at most x. This satisfies the Gaussian law. So, as limit n goes to infinity, this turns out to be equal to minus infinity to x of the integral corresponding to the Gaussian distribution. So, you have 1 over root 2 pi minus dt. Okay, and in the probabilistic sense that we had started talking about, this Erdos-Kac theorem can actually be interpreted as a central limit theorem. You in your second year course that Chandrasheel taught, you people learnt the statement of central limit theorem. You did not learn a proof. You will probably learn a proof in Professor Momanty Podder's course, and you will also learn a proof in this course, and you will also learn to relate it to the study of omega of n. So, this is basically this, depending on your taste, either the Hardy-Ramanujan Turan theorem or the Erdos-Kac theorem is the theorem 0 of probabilistic number theory, and in our next class we will jump properly into these theorems. So, I will stop for today.